Welcome to Field Notes, the monthly podcast of modern steel construction, the monthly magazine at AISC. I'm your host, Jeff Weisenberger, Chief Editor of Modern Steel Construction, and this month's guest is Ron Klemencic, Chairman and CEO of Magnuson Klemencic Associates in Seattle. Ron's worked on projects in 24 states and 23 countries, including multiple block developments of up to 7 million square feet and towers well over 100 stories. He's also a champion of the SpeedCore system, which we'll touch upon shortly. Welcome, Ron.
Yeah, good morning.
Morning. Well, let's start from the beginning. I mean, obviously, we're going to talk about SpeedCore and a lot of other things, but first off, where are you from? Where did you grow up?
Well, I grew up in Racine, Wisconsin, which is a small town of about 100,000. Maybe these days it's more like 80,000. It's about an hour north of Chicago, right on Lake Michigan, and its claim to fame is the headquarters for the S.C. Johnson and Sons company, which makes all kinds of home products like Agree shampoo and Off bug spray and what have you. But why any of that's relevant is they were also patrons of Frank Lloyd Wright. So my hometown is filled with buildings designed by Frank Lloyd Wright, which was, something I grew up around and was, I suppose when I was a kid, I didn't really know what any of that meant. But later in life, I learned to appreciate it immensely.
You said Racine. When I think of Racine, I think of Danish Kringles.
Yes. Yeah. I still order them to this date.
I was going to say, which is your favorite bakery?
O&H.
I was going to say there's that one and at least one or two others that I know, but O&H is the one I'm familiar with too. That's great to hear.
Yeah. Here in Seattle, I can get it in 24 hours from O&H, and my favorite flavors are almond and cherry. So anyone that's out there listening, go on your website and Google O&H Bakery, Racine, Wisconsin, and order the almond-flavored Kringle. You won't be disappointed.
Yeah, and I can second that. Yeah, it is pretty remarkable. Well, that's great. So, I mean, you talk a little bit about growing up in a place with a lot of Frank Lloyd Wright homes. Can you tell me about what made you want to get into buildings and structural engineering in the first place? Was this something that you said, when I grow up, I want to be, or was it something you discovered closer to college or in college even?
Yeah. So my story is this, that when I was a kid, a little kid, right, I would build cities in my sandbox with my matchbox cars and my buckets and shovels, and I would build cities and then I'd destroy them, and then I'd build another city and I'd destroy it. And building cities was like fascinating to me as a really, I don't know how old I was, 7, 8, 9 years old, maybe 7 or 8. And kind of also around that time, we had a lot of family in the Chicagoland area and would go down and visit them with some frequency. And my dad would take me downtown occasionally. And at that time, they were building the Sears Tower. And I was just totally blown away by the construction of the Sears Tower. It was just totally fascinating to me. And as a young kid, I thought, wow, I want to do something like that. That's super cool. In about middle school, I thought that all meant being an architect. Mm-hmm. And so I started drawing pictures of houses and buildings and floor plans and convincing my family I needed to be an architect. And then it turns out I had 2 uncles that were both civil engineers. And they sat me down, I think, early high school and explained to me what an architect did and what an engineer did and kind of how the whole building industry worked. Mm-hmm. And it was with that kind of guidance that it was pretty clear to me that my brain was wired for science and math and technology and not so much for art. And so I chose a kind of engineering path, probably, 10th grade, 11th grade. So I pretty much knew I wanted to design tall buildings or design buildings and set off to be an engineer, in high school. And then the rest is history.
Okay. And then you ended up going to Purdue University. Is that right?
Right. Yeah. I was undergrad at Purdue, graduated in 85, bachelor's in civil engineering, and then went on to get my master's degree at Berkeley straight away. I did the one and done program at Berkeley, coursework only with a comprehensive exam at the end, and graduated Berkeley master's degree in structural engineering in 1986. Okay.
Excellent. Well, going back to what you were saying about your childhood, I think it's pretty telling and interesting to me, especially because I at one point wanted to be an architect, but I had some architects kind of talked me out of it at a career fair. But the fact that you had uncles or, family members that were into civil engineering and could sort of say, look, it's not just about this part of it. This part of it's also incredibly important. Well, I mean, that's a pretty great influence to have early on.
Yeah, it was fantastic. And, further to that end, it's maybe sounds pretty geeky, but when I got into high school calculus, I was so super excited to understand that you could explain the world through math. To me, that was like amazing that you could, through equations and mathematics, explain the physical world. I thought that was so cool. So that was really prompted me even more to want to go into kind of engineering and follow the technical side of things.
Sure. Well, yeah, that's quite the revelation. One other thing, when you were talking about the sandbox, that's pretty great too. At an early age, you kind of figured out the whole concept of design iterations. A lot of kids would just build it and say, "Oh, this is great, don't touch it." But you're like, "No, let's take this down and build it back again and make it better or different." So
yeah.
That's pretty cool.
What's also maybe telling about that whole story is that's in the pre-Legos era.
Wow.
These days, a lot of the young people that we hire out of school have a Legos story.
Sure.
Their kid, their parents bought them Legos and they built things out of Legos and they thought that was cool. Well, when I was a kid, there weren't any Legos. Sandboxes were the tool of choice.
Right. Yeah,
it was always kind of almost a religious activity. Every spring, my mother would take me down to the supply store and we'd buy a couple of 50-pound bags of sand, and it was so exciting to get the sand and haul it home and fill up the sandbox for the year. Fresh sand.
Right. And then when you saw Legos for the first time, you're probably like, "Oh man, my mind is just blown."
When that was the kind of Lego Lake toy that we had when I was a kid was something called Lincoln Logs.
Oh, I remember those.
Yeah, I had a bucket full of Lincoln Logs. So.
Yeah, very cool. Well, so let's talk a little bit about SpeedCore. I think most people have an idea of what it is or have at least heard about it, but just for those who haven't, can you just provide a brief description of the concept?
Sure. For the last couple of decades, 3-4 decades, I don't know, a long time, we've been designing lots and lots of buildings, tall buildings, that have a reinforced concrete core as their bracing system. And then surrounded by structural steel floor framing. And there's a long story as to why that's even the case. But anyway, if we take that as a baseline, what we knew from building dozens and dozens of these all over the world was that the construction schedule was impacted significantly by the cycle time on the concrete construction of the core. And on most projects, steel erection was delayed. The start of it was delayed in order to get the concrete core out far enough ahead so that the structural steel erection wouldn't catch it. And that we took on as a problem statement. Like, how do we change that? How do we fix that? How do we make it go faster and avoid having this scheduled lag in the start of steel erection? And that was the impetus behind SpeedCore, was to come up with a steel-based structural system that offered the strength and the stiffness and the kind of architectural dimensional parameters that we needed for these taller buildings, but also afforded the speed. And that's kind of where we got to with how we got to SpeedCore. Now, what is it? It's a prefabricated modular wall system where two steel plates are separated by a field of, I'll use the word cross-tie rods, but they don't need to be rods. They could be flat bars or pipes, or they could be anything that interconnect the two plates. And if you take the analogy of an ice cream sandwich where the chocolate cookies are the steel plate, and then you fill those two steel plate chocolate cookies full of concrete, the ice cream, if you will, that composite section is the wall panel that ultimately braces the building. So there's no formwork, there's no reinforcing steel, there's no embed plates to place in the formwork, it's a much, much simpler and faster system to erect.
Right. As we've seen, sure. And I was going to ask about projects as well in a minute, but just one other question. So, when it comes to a concept like that, obviously any new concept, especially in an industry like construction, is going to be met with skepticism at first. Can you just talk a little bit about what it was like getting all parties on board with it?
Yeah, that was a process that required a lot of tenacity, a lot of just sheer will.
Mm-hmm.
I reflect on this often, that my forefathers in our company, the likes of John Skilling and Les Robertson and Jack Christensen, kind of back in the 50s and 60s and 70s, when they came up with a new structural engineering idea or concept, they'd do all the math and the physics and they'd prove it out to themselves. And occasionally they'd actually do some physical testing mock-ups, if you will, but mostly just for themselves.
Mm-hmm.
And then they design the building and they build it. These days, you can't do that anymore because of the approvals processes, and in particular, kind of the unfortunate litigious world in which we live. We've got to have everything kind of buttoned down before we do anything new. So that means you need to do a whole pile of physical testing and research before you implement anything new. So it was about 2005 when we first decided to launch a research program. We'd already had this idea back in the early 2000s, but it was about 2005 we launched the idea of we need to get in the lab and we need to prove this out. We did all the math, we ran all the computer models, but we need to confirm our calculations with physical testing. Mm-hmm. So that's when we launched things off at Purdue to do the physical testing. And so here we are 17 years later, we're still in the lab making it better, mm-hmm. enhancing it. And then along the way, of course, as we designed these couple of buildings now and got them approved and built, the approvals process through the building officials and the peer review panels was pretty rigorous. Not unusual in today's world, but because it was a brand new system, maybe even more rigorous than normal.
Sure. Okay. Well, and so from what I understand, there are currently, because I've seen one in person. Actually, I got to tour it, and I know the other one is the first one is Rainier Square in Seattle, which is right next to your office, and then 200 Park. I don't know if that's still the current name in San Jose.
Right.
Sure. And I know both projects were erected compared to that baseline concrete core that you were just talking about before, that we all know, like months faster. Is that correct?
Right. Yeah. So in the case of Rainier Square, we had taken the design of a traditional reinforced concrete core all the way into design development. Mm-hmm. So we had, it wasn't a complete design, but it was a pretty advanced design with a traditional system, when we all decided, along with our client, that we needed something better, faster, cheaper. And that's where we started studying SpeedCore as kind of an alternative system, and went through a very rigorous analysis with the contractor and the subcontractors to, at least on paper, convince ourselves that there was value there. And early predictions were that it was going to be cost neutral and it was going to save about 8 months. So that inspired the owner to just say, forget the concrete core, let's proceed. What Rainier Square proved out when we were all said and done is it was indeed cost neutral, and it saved 10 months on the schedule. So that was a huge savings. Now that's a 58-story building with 7 basements, so it's a very tall, lots of floors building. Mm-hmm. On 200 Park, it's only about a third of that height. It's 20 stories. Mm-hmm. And on that building, just be given the unique nature of the architecture and the fact that it's in San Jose on kind of poor quality soil and it's close to the San Andreas Fault, blah, blah, blah. The seismicity was very high. Anyway, long story short, on that project, we ended up saving about $10 million in cost and 3 months on the schedule. And that was the prediction from the contractor when we assessed concrete versus SpeedCore, and that was actually realized. At the end of the day, the building's complete now. And we did, in fact, save $10 million and 3 months on the schedule.
Yeah, that's incredible. Well, looking forward, what's on the horizon in terms of future, or upcoming SpeedCore projects?
Yeah, there's several on the boards. A couple more here on the West Coast, mostly in the Bay Area, in Oakland in particular, and maybe even more, and sooner than that. We have a building designed, reviewed, and permitted in Boston.
Right.
All set to go. The only thing holding it up is it's a spec office building, and the developers in lease negotiations with a would-be tenant. So until the tenant signs the lease, we're kind of in a holding pattern.
Right.
But hopefully that will happen soon, and that will launch that building.
Right.
They are on site already doing some enabling work. So it's a for real building. It's more a question of not if, but when. It's going to happen here, hopefully shortly. And then there's a couple of more buildings in Boston that we're designing right now that have SpeedCore elements as part of the design. And my distinction there is that the system in those buildings are mostly structural steel brace frame and ordinary concentric brace frame. But because of some unique geometries of the building, we're using a couple of singular SpeedCore shear walls to help stiffen the system, and in particular, stiffen it in torsion. So this is a good example of, we call it SpeedCore, and it seems very specific in its application, but it's really not. It can be used in part or in whole. It can be used in a variety of geometries, and we're proving this out right now on another project in Boston.
Okay, well, that's excellent. And on that note, obviously, you like you said, in design and then in the lab, you're still trying to constantly improve the concept. But from the first two buildings, SpeedCore buildings that have been completed so far, any interesting lessons that you learned from those in terms of tweaking design or easing constructibility or erection?
Yeah, this podcast isn't long enough to cover it.
We can save that for another one.
Yeah. There's countless stories and things we learned. I might highlight just one or two things that we're currently working on in the lab. Probably the most important and significant of those is working on a range of bolted field splice connections. The two buildings we built today had welded field splices. And we know in many markets around the U.S., field welding is not a desirable means of attachment, that bolting is preferred in many places. And so we've proven out a bunch of bolted connection alternatives on paper, but we're in the laboratory at Purdue and at Buffalo right now doing full-scale tests of these bolted splices just to prove out the math.
Okay.
And those tests will be done probably around the first of the year. So starting 2023, we'll have a whole menu of choices for fabricators and erectors to consider for bolted field splices. So that's one big advancement that we're working on. The other one relates to fire protection.
Okay.
And we're kind of partway through that research project. We've already proven out through fire testing that the wall panels themselves need not be spray fireproofed so long as they meet certain design parameters in terms of wall thickness and plate thickness and cross-tie spacing, what have you. What we're in the lab doing now is looking at the beam to wall connections.
Okay.
And how those need to be modified, frankly, in order to eliminate spray fireproofing or any fire protection for the beam wall connections. And that work's probably going to be published in the spring is a reasonable guess. So that's ongoing. There's a never-ending list of things to think about. I laugh frequently with my research colleagues at these various universities. The best researchers and professors always end their research with a list of questions yet to be answered.
Right.
That's how they stay in business.
No, of course, no, it makes sense, right?
Yeah.
Well, yeah, looking forward to hearing the results. Like, I mean, obviously, SpeedCore is an innovative idea, and you're clearly somebody who embraces innovation. So, aside from SpeedCore and its never-ending list of projects, so to speak, I'm curious, what other big ideas do you have up your sleeve? Is there anything you can tell us about, or at least tease us with?
Sure. We're always working on the next thing. Maybe two items, one brief and one a little bit longer. The one that I'll keep very brief is something we've been working on for a few years now, is performance-based wind design.
Right.
And it's basically taking the performance-based seismic design framework and methodology that we've been implementing now for almost 30 years and adapting it to kind of wind demands. And in doing so, allowing some modest nonlinear response of buildings in extreme wind events. And so we've already designed and have under construction the first tower designed this way in the world. It's in Austin, Texas.
Okay.
And we have three others on the boards right now that we're advancing using this methodology. And the bottom line is that it saves somewhere between 5 and 7% of the structural cost of the building using this calculation methodology. Basically, it's a more rigorous calculation methodology. So that's one. The other one that's maybe more interesting and relevant to AISC is something that is, I call it a companion to SpeedCore. And something that we're all AISC, the rest of us working on it, are calling fast floor. And fast floor takes its inspiration from the shipbuilding industry.
Right.
Where, of course, when was the last time you saw a slab on metal deck on a ship? But yet ships solve all the same problems as mixed-use buildings, right? There's a hotel, there's restaurants, there's theaters, there's pretty much every use under the sun on a cruise ship, yet it's all made of steel. And so the idea here is to formulate a floor system that's prefabricated, modular, erects very, very quickly and simply, and requires no concrete. And so we're in the laboratory right now. We have a team led by Jerry Hajar at Northeastern University. And researchers at Iowa State and Virginia Tech and Johns Hopkins, a whole team of researchers working on what exactly does that look like. So we're about ready to start some vibration and acoustics testing. And hopefully, if that proves successful, then we'll move on to some other more rigorous testing of strength and diaphragms and what have you. So we're in beginnings of a multi-year research project on fast floor, but that's super exciting. If we actually realize our ambition here, it will prove to be another kind of step function in increasing the speed of construction. The early estimates from a couple of our general contractor friends who have evaluated this say that it will reduce construction time by about 30%.
Wow.
So it's a big step function.
Oh, indeed. Yeah. Looking forward to hearing more about that. Yeah. It sounds very promising. Well, I want to switch gears a little bit and talk about Magnus and Klemencic Associates. I mean, obviously, your name is part of the firm's name. And can you tell me a little bit about your history with the firm? And can you also explain the so-called temporary nature of the firm's name?
Yeah, fair enough. So I joined Skilling, Ward, Magnus, and Berkshire in 1992. So it's now 30 years that I've been here. The company itself was founded in 1920 in Seattle by a gentleman named William Witt. And he oddly was a immigrant from Wisconsin.
Okay.
who came
from Wisconsin. Okay.
Yeah, he immigrated from Wisconsin to Seattle and formed an engineering company here in 1920. And so we are currently on name number 7. And the firm's name has changed 7 times in the course of that 100 years, always to be representing the kind of active, most senior leadership. So today that's John Magnuson and myself. And it will change again. There'll be a name number 8. When that happens, I don't really know. And what the name will be, we don't really know yet, but it will happen. It's part of our culture. And what really fuels that for us is that in the kind of niche that we play in the world, we design, very complicated, very large projects of all sorts around the world. There's really a very small community of practitioners that do that regularly and consistently, and we all kind of know each other. And having that personal connection and relationship with our clients and with our architect colleagues proves to be important. And as a business strategy, having the named partner in the room to kind of vouch for the design, if you will, is a point of difference. A lot of firms can't do that these days. Most firms can't do that these days.
Right.
In particular at the level that we play. And so this is part of the overall strategy of the company. We're very independently minded. We're very kind of committed to how we go about our business. And so while we regularly are solicited by companies wanting to purchase MKA to assimilate into, any one of the large AE firms that you could list off, the answer is consistently no, thank you. We're very happy being independent and doing what we do and how we do. And that's kind of part of just who we are.
Great. I think it's a great strategy. Well, and, speaking about in the engineering profession in general, from those giant firms to smaller firms to you all, and you've been with MKA since 1992. What are some of the, biggest changes you've seen to the profession, to the engineering profession, over your, 30 plus years, I suppose, in studying and practicing engineering?
Right. Yeah, there's a constant evolution of things, for sure. What's the biggest change? Wow, that's a really tough question. I don't know what's the biggest one. The thing that pops in my mind immediately, I suppose, is the speed at which things happen, communications in particular. And related to that speed is kind of an expectation of that speed. It used to be that questions would come from a contractor in the field and we'd have a day or two to answer them. Now we have like a minute or two.
Right.
I mean, I'm being a little facetious, but kind of through and through the whole process of design and construction, the speed of communication, of course, facilitated by all of our technology, has gone berserk, basically. In some ways good and healthy, in other ways not so good and healthy, because occasionally you need to think about things for more than a minute. And so there's some increased risk with that speed. But that's the one big thing that comes to my mind from the beginning of my career, when fax machines had just been introduced into the workplace with the thermal treated paper.
Wow.
And we thought it was really cool to be faxing things back and forth to one another, because that was brand new technology. I talk to my kids now about fax machines and they look at me like, what the heck is a fax machine?
Yeah.
And why would you ever use one? Or rotary dial phones, right? When I first joined the firm, we were just getting touch-tone phones, which was like a huge advancement. But of course, it's this box sitting on your desk that's wired to the wall.
Yeah.
These days, no one even contemplates that sort of stuff anymore. So the speed is a big deal.
For sure. Yeah, no, I think my kids have grown up in the two houses they've lived in without ever seeing a landline. They know what it is, but at least not in their house. Maybe at grandma and grandpa's house or somewhere else, but right.
Yeah.
Well, so, and then just I want to talk a little bit about Seattle now. So you've been there since 92 or a little bit before that even?
Yeah, I moved to Seattle in 1988.
Okay.
Well, a couple years before I joined Skilling.
Gotcha. So, you've been there long enough, obviously, that you're almost a local at this point. But I was just going to ask, what do you enjoy most about the city and the area?
Yeah, Seattle is a beautiful, beautiful place physically. Mm-hmm. The mountains and the water and the snow on the tops of the mountains and the green forests everywhere. It's just a very beautiful place in the country to live. And then associated with that, all of the outdoor activities from hiking to biking to running to skiing and golfing and just being outside in the fresh air and the great Northwest environment. And yes, we all have our rain gear, so come rain or shine, we're out there.
Right.
It's just a really great, comfortable place for me to live. I really enjoy the kind of vibe of the place. It's a bit more relaxed and easygoing, I suppose, as compared to other places in the country. And, there is the clouds and the rain, and you got to deal with that. But I travel enough to not have that be too big of a deal for me.
Sure. Are there? Yeah, and I think I was told once that it's not so much that the average rainfall in Seattle is so much higher than anywhere else. It's the fact that it's just so much more constant.
Yeah. Well, I don't know what the exact numbers are, but I think the factoid somebody told me once that it rains more numbers of inches in Chicago than it rains in Seattle. It just is, more constant and cloudy in Seattle. In fact, here's a funny statistic somebody told me years ago. I don't even know the numbers anymore, but the punchline is that the most numbers of sunglasses per capita are sold in Seattle. And the reason is we only need them for like 2 weeks a year. And then you put them somewhere and you lose them and you can't find them and you need to buy a new pair.
Right.
So we're constantly misplacing our sunglasses because we only need them for a few days.
Right. If you lived in Florida or, or Colorado or California, you'd have them on you all the time and you'd never lose them.
Yeah.
Gotcha. Now, this is why I always buy cheap sunglasses because I lose them no matter where I live. Okay, so you moved there in the late 80s. I got to ask, you moved there right when the grunge scene was really taking off. Or are you a grunge fan? Is it impossible not to be if you live in Seattle?
Yeah, I wouldn't necessarily say I'm a grunge fan. I'm a fan of all sorts of different kinds of music. So I like certain parts of grunge. I wouldn't say I'm part of the grunge scene, though.
Oh.
But there's a lot of other interestingly famous musicians from Seattle that people don't really realize, perhaps like Quincy Jones or Kenny G. These are really profound musicians that all came from the Seattle music scene. So there is a deep-rooted music scene here, grunge being probably the most well-known.
Sure.
With Pearl Jam probably leading the pack.
Yep. Well, yeah. And Pearl Jam, Eddie Vedder has a Chicago origins. Yeah, I ask because, of course, like you said, it is sort of that one style of music that's so closely associated with the area. And it was sort of becoming the thing right when I was in high school and college. So we were all walking around listening to it with flannel shirts on.
Yeah, fair enough. Yeah, well, Eddie's very active in the community. I see him pretty regularly out and about or on airplanes to and fro from Seattle. So he's still in the community and still really out and about and active.
That's great to hear. That wraps up another edition of Modern Steel Construction's Field Notes podcast. Again, our guest this time around has been Ron Klemencic of Magnuson Klemencic Associates, and I'm your host, Jeff Weisenberger. Thanks for listening, everyone.